Here, this is the outline of our talk, and I will focus on the first part. I will introduce what is SAN networks and what is node relevance, and Tyler will focus the mid part of this talk. Briefly, SAN networks is networks with positive and negative links, and the positive links could be friendship, trust, and the negative links is the opposite meanings of the links like enemies, foes, and distrust. I will give actually actually there are some websites, social media websites. Users are allowed to explicitly establish negative links and positive links. So one is opinions, where users can establish trust and distrust links to others. And another one is /Derr. So this is a technical news. Users can share technical news, and also users are allowed to create friendship and also false links with others. And another one is the Bitcoin exchange networks, because people can feel free to exchange Bitcoin, so they use the positive and negative links to indicate how trustworthy this user during the transaction. Okay. Although there are three websites which allow the positive and negative links, actually the access controls of negative links are very different in those three websites. One is, for example, in the Bitcoin exchange networks, basically users can, the negative links are visible to the public. So basically everybody can see the negative links. And for the /Dot, only the users who log into the system, you can see the negative links. And for opinions, so basically only the server allow negative links. Even for the users who log into the system, they cannot see the negative links. Actually, actually the access controls are very different in those three websites. So here, a larger question is, will this affect the network structures of SAN networks? Actually, we found a lot of differences when we can the visibility of negative links are different to the public. And here is one finding we think is quite interesting. So we studied the reciprocity of positive and negative links. So basically, is if I give a positive link, how likely the other user will give a positive link back? The same for negative links. And here are the results. We can say actually in Bitcoin networks, the reciprocity of negative links are very high, while /Dot is lower, and the opinions are even lower. So what does this mean? Actually, if we connect this to the access control, we can get some evidence. So basically, somehow revenges happened here, because in Bitcoin, basically the negative links are visible to the public. So we can observe a very high reciprocity. But for /Dot, you can log in and you can see the negative links, and probably you will give a negative links back. And for opinions, because excuse me, negative links are invisible, so we can observe a very low reciprocity. We have those 4 data sets, and later on Tyler will share where you can access those data sets. Okay, and in this talk we just share this difference. Actually, we find many more, and if you are interested, we can talk offline. So traditionally, we a network will only have positive links. For example, if we have n users, probably theoretically we have n square pairs. So for those pairs that don't have links, I think most cases is not equivalent to negative links. But previously we give 3 sites which can explicitly have negative links. But actually, the negative signals are everywhere in social media. For example, in Facebook, we can unfriend someone. This is one type of negative links. In Twitter, we can unfollow someone. And in Google Plus, we can uncircle. And in LinkedIn, we can remove connections. And in YouTube, we can unsubscribe. So basically, negative links are everywhere. So we should make some efforts on the networks with both positive and negative links. So the next question is why we care about load relevance. So the definition of load relevance is we try to measure how similar 2 loads are in a social network. Because typically the links in social networks are very sparse. That means there are a lot of pairs that don't have any links. So if we can use the network structure, we can get the relevance of 2 loads. Basically, that can help a lot of applications. For example, for definitely one straightforward application is link prediction, right? So get the load relevance, we can somehow to the 2 things we can consider can improve load classification. So one is we can get a fine-grained relation between 2 loads because typically in the real world we only have the binary relations, and also because of the sparsity, a lot of merges will fail. So if we can get the relevance between any 2 loads, we can somehow mitigate the data sparsity problem and improve the performance of node classification, community detection, and even for search and recommendation, especially the social recommendations. For example, because the cold start and data sparsity problem is well known for recommendations, right? So for example, if typically we will have the feedback from users on some recommended items. If there's low feedback, we can not make any recommendations. But however, if we can get some users in the network that are similar or they are closer, they have similar preferences or interests, we still can make recommendations even you don't have any feedback to the items we want to recommend to you. So that's why we also believe it can improve search and recommendation. However, most existing methods are designed for unsigned social networks. And roughly, we can have 2 groups of methods. One is the local methods, some famous one including the common neighbors and something traditional preference, attachment, and so on. And the second group is global methods. Basically, we consider the global structures of the network when we measure the relevance of 2 loads. For example, the random walk, the cats, and so on. Okay. Typically, those methods are designed for network with only positive links. For example, in this case, we can get common friends and so on. But when we introduce negative links, how can we define those things? Actually, most of them are not applicable when networks with both positive and negative links. Then, a large question here is, why? Should we need new methods for signed networks? So if we need a new, can we extend them to signed networks? And when we extend them, what surprise we can get? So that's, I think Tyler will introduce. So my questions will be answered by Tyler, okay? Tyler.
Can people hear me in the back? Okay. So going into the node relevance. So as Dr. Tang had just talked about, so negative links are unique to signed networks, so they're not found in the unsigned networks. And a not so intuitive question that we have is, how can we use these node relevance measurements from unsigned networks when we have a signed network? So if you kind of think about it for a minute, that some of the issues are that in unsigned networks, we only have one type of link. And so we could maybe treat all the edges the same. And another issue is that typically you can normalize the outputs between 0 and 1 for node relevance. But in a signed network, we would want that to be between -1 and 1 because we can have a negative relevance to someone else. So with the first issue, we're going to try to figure that out. So the first resolution could be if we remove all the negative links and only use the positive links. Another thing we could do is just treat the negative links the same as the positive links and just use that resulting network. So the second issue, if we're normalizing between 0 and 1, how do we find these negative associations if the output is between 0 and 1? So one thing we could do is we can make an assumption that all negative links are weaker than the positive links, or you could actually make the other one as well, that negative links are stronger, but this actually empirically tended to work a little better. So what we want to do is find some threshold t between 0 and 1 and define that as kind of like the split between negative and positive relevance. And what we can do is, since we have our like training network, we can basically look at the positive and negative links, look at the resulting the relevance measurement that we get for those, and then try to define this threshold to best classify the negative and positive links from the measurements that we get. So if we have between 0 and t is negative, and then t to 1 is positive, we can take a unsigned 0 to 1 node relevance and map that to the -1 to 1. But a better solution would be just create new relevance measurements specifically designed for signed networks. And so the benefits would be it's already between -1 and 1 by design. We could base it on things like balance theory, so social theories that are related to signed networks. And we could use other properties that are unique to the signed networks to improve the performance as compared to just using an unsigned method and then mapping it to the range that we want. So quick overview of the structural balance theory. And so it has roots in social psychology from the mid-20th century, and it's based on the ideas of a friend of my friend is my friend, the enemy of my friend is my enemy, and so on for the other two cases. And we can see that basically then all of these triads, that we should have an even number of negative links based on the social psychologist interpretation of the way that users interact, not just in social networks, but just kind of in social settings. And so you can see here that the A and C are balanced because they have an even number of negative links as compared to, for example, B, that this is unbalanced because the bottom link is negative, and if they are both friends with the one at the top, that it would seem unstable that eventually one of them would flip to being enemies. So here's some quick notation for the rest of the presentation. Basically, R is the matrix we're using for the node relevance. A is just the adjacency matrix. We use in, out, and pluses and minuses to denote the in and out degrees and the positive and negative edges. And N we denote as the set of the neighbors for a given user. So jumping into the local methods, the first one, quite common, is the, oddly enough, common neighbors. So this definition of node relevance in unsigned networks is based on the idea that if you have common friends with someone else, that you're likely to have a strong relationship with them. And so it's just measured as you take the neighbors of user I and user J, you get the intersection, and the larger that is, the stronger the relevance is between them. So to visually see that, between I and J here, their relevance would be 2 because they have 2 in common connections. So in a signed network, what we'd want to do is basically look at the number of common neighbors that are either in agreement or disagreement. So here we can see that if both I and J have a positive link to a common person, that would strengthen a positive relevance between them. But for example, if I thinks of someone as an enemy and J thinks of them as a friend, well then that would be more of a negative relevance between them because it's a disagreement. So in an example coming up, that the connection is we're trying to force more triads to be balanced in this situation. So here, between I and J, we can see this figure where red denotes negative links, blue is positive links. So they have 2 common friends, so that's an agreement. They have 1 common enemy, and they have 1 disagreement. So with assigned common neighbors, they would have node relevance of positive 2 because the 3 agreements and 1 disagreement. So the Jacquard method is another common method used in unsigned networks for node relevance. And it's almost identical to the common neighbors, but we want to take into account that a very popular user might have a lot in common with someone else, but that might not be equivalent based on the number of users they're connected to or their degree. So what we will do is normalize by the union of their neighbors. So seen in the figure, we're basically saying that here between this I and J, it would have a stronger relevance to each other than in this case, because this I and J have so many more connections that only having 2 in common isn't as strong as the 2 in common on the right-hand side. So adjusting this to the signed network case, it's almost identical. We're just normalizing by the union of all of them, so the positive and negative from both sides, and using the signed common neighbors. Connection is still the same to balance theory, that we're trying to make more of these triads balanced. And by using this kind of relevance, that's what it would be forcing. And the last local method is the preferential attachment. So here, it's the idea of that the rich get richer, or in social networks, you have some very famous people that have lots of followers, but most people, the large majority, have very few. So you get this power law distribution then. And so the node relevance score is basically just multiplying the degree of the 2 users. So it's kind of the idea of if you have a lot of connections, you're more likely to get a lot of connections in the future, and so your relevance to everyone else would be slightly increased. But mapping that to signed networks, what we're going to do is split that into the A plus, A minus, which is just the adjacency matrices representing the positive and negative links. And we can define the unsigned preferential attachment in both of these respective networks that we've created. And now, to define the signed preferential attachment, what we can do is say, we first want to decide the sign. Is it going to be a positive or negative relationship between them? And then from there, we want to define a function that will take in these two values and determine the strength of this relevance. So one straightforward, easy way would be to look at the strength as being the positive minus the negative and the absolute value of that. But empirically, we found that taking the maximum of the two and then using the sign as either +1 or -1, that actually tends to work better empirically than the kind of straightforward way of looking at the difference between them. And the connection here is that the sign network property, both of the networks, the positive and negative, both are shown to represent the power law distribution. So it's reasonable to split them into the positive network and the negative network because they both follow this same kind of distribution. So the global methods, these are a little bit more interesting. So the first of which is the unsigned cats method. And the idea here is that we're looking at all of the paths between two nodes, and a shorter path has a stronger weight than a longer path. So here we can see that we'll use beta as a way to kind of like discount the longer the path, the less important it is. And here we're saying the number of paths of length L between I and J. So the relevance between them, we would just sum up the number of paths at the different lengths, and discounting a longer path isn't as meaningful as a short path. We can rewrite that to a different form where here this delta is basically just to have a self-relevance, and it's just defined as the identity matrix. So when looking at relevance to yourself, it maintains at least a positive relevance. So a signed version of that, what we would want to do is basically keep track of the number of balanced and unbalanced circles between them. And the way we can do that is use this slight modification that we're saying for a given length L, we'll look at the number of balanced cycles between these two users, I and J, and then subtract off the unbalanced. And so the idea between that is if you have a balanced path between I and J, that then it would have to be a positive relationship between them to keep that cycle as balanced. But if it's unbalanced, which would mean a odd number of negative links between them in that path, that it would force a negative relationship between I and J to keep that cycle as being balanced. So that extra negative would make it an even number. And the way that we can define these B and U matrices is, got jumbled together, but so B is defined as the positive adjacency matrix and U as the negative adjacency matrix. And so we can use this recursive definition of saying, just look at this one first. So for the balance of a given length, L, we can look at the number of balanced of L minus 1, and then since A is symmetrical, we can just take the product then between B and A. So what that's going to find is if between I and K there were, say, 7 balanced paths, that when multiplying by A to get to J, it would just take that into account. And we're saying plus, so an unbalanced and a negative. So if we had between I and K in this scenario an unbalanced path, the reason we're using the A negative here is because that will add one more negative to make it balanced. And if it was already balanced, we would just multiply it by A positive, so that's adding one more positive link, and it would still remain balanced. And then this case, for the unbalanced, it was just the opposite, that if it was balanced, we would want a negative because that would force it then to switch to be unbalanced. And actually, we note, you can actually prove that the unsigned cats method is actually equivalent to this. Isn't that straightforward, but they do end up actually being equivalent then. So we had mentioned SimRank as being one of the other global methods, but this ASCOS method actually identified a problem in SimRank. And so it fixes the issue that odd length paths between users in SimRank would basically not be accounted for. So we thought this would be a better method to expand upon. And the idea is that two objects are considered to be similar if they're referenced by the same object. So in this scenario, we're looking at the relevance between I and j is based on the normalized neighbors of I. And so for every k that is coming into I, we look at what is their relevance to j. So between I and j, everyone that is coming in to me or following me, then what would also they think of j, and then that's how we relate I and j. But so that actually was the baseline, and they came out with a version for weighted networks, which they denoted as ++. And what this does, it changes the mapping. It takes into account the weight rather than just +1 or 0 for a link or no link. And it normalizes here. So it's basically that rather than saying 1 over the degree, it's now looking at the weight of that IK edge over all of the IQ, for Q being all of the incoming links. But the problem here is that it's undefined if a user has the same number of positive and negative incoming links, because if we just take the summation here, we could get 0 if they have the same number of positive and negative incoming links. So that's one issue of directly just using this with a signed network. And actually, it can be proven that in some cases, the relevance ij that comes out of this equation contradicts balance theory when looking at the rij, aik, and rkj. So we proposed some modifications where we want this triad to, of course, maintain the balance theory. So here I'm just saying again that this mapping, if we use it directly, you actually get 3 times as strong of a value for a negative link than a positive link. We could change that, but we just left it since these signed networks usually have about 80 to 90% positive links, that it's very imbalanced on the number of negative links. So by treating the negative links 3 times stronger, it actually helps leaving that there as compared to removing this part of the equation. And we propose just to take the absolute value. And it seems that such a simple change might not make that big of a difference, but changing this to the absolute value forces all of them to be positive. So I'll move a little bit quicker. That getting set up took away some of the time. So another one is the random walk with restart. It's a fairly common global measurement, and here is the formulation. But with the signed random walk, what we're going to do is redefine the way that we're setting up this transition matrix. And the idea is that if the akj is greater than 0 and ik for the relevance is greater than 0, what we'll do is use that to push the Rij to also be positive to make a balanced triad. And similar cases, if AKJ was negative and this was positive, we would want to push this to be negative to maintain the balance. So we'll just define the matrix W as the absolute value of the link over the degree. And what we can see here is basically just this idea, that if we take the sign of the link times the weight and the relevance, that this is our Ij, Kj, and Ik triad, and we want that to be positive. And so here we can update II and Ij slightly differently. So with II, we want to maintain this self-relevance to be positive. So we always force that +1 here, and we don't have that between an I and a J. And that can be proven equivalent to this closed form solution then for the relevance matrix. So the applications, I'll quickly go through this. So link prediction, what is it? We're trying to figure out between two nodes, what is the sign? Is it going to be a positive or negative between them? Why is this important? Well, it's pretty useful to know when recommending of things like friendship recommendations or foe recommendations. And what we'll do is try to figure out what these red links, are they positive or negative? And it's previously been shown in other works that node relevance work pretty good for trying to do link prediction. So by using this application for the different measurements, it's a way to determine the quality of the different measurements and compare them. So how are we going to do that? Well, we can just look at the sign of the relevance. So if the relevance, for example, was 0.4, we can just say that that would be a positive relationship between them. And with the unsigned node relevance, what we would first do is use this mapping function, which is what I described before, where we're finding that t value, and we're then going to map it between -1 and 1, and then take the sign. So here, for time's sake, we basically see, in a nutshell, that the global methods perform better, and the best in each of the 4 data sets was one of our signed variations. In the directed setting, it's also the signed random walk that across the board performs the best. Tie strength is the problem of between two users, we want to determine the strength of their relationship. So if in the network we have a negative link, we want to infer how strong is that negative link. So why is this important? Well, it can lead to a more detailed version of that network, and some impact would be that you can get a priority ranking of friends, and it can be used for other applications of knowing which of your connections are your weak versus your strong ties. So with this problem, how are we going to solve it? We can actually just directly use the relevance measurement. And here we see that actually the local methods perform better than the global methods on the tie strength. And that could just be because when looking at the strength of relationship, the global information really doesn't matter as much as just having that local information around you and your close people. So node classification, we're trying to infer information, and for time's sake, it seems we're out of time, so I'll skip through this part. But the general idea is we're trying to classify users as a specific type. So in opinions, a user can be classified in one of these categories, and so we are doing a 15-class classification. Using the similarity matrix instead of the adjacency matrix, we can get some improvements. And conclusion is that dedicated efforts into assigned networks is very useful and has a performance improvement as compared to using unsigned measurements. Global methods perform better on link prediction. For the tie strength, It's usually the local methods. For node classification, global methods perform better with more information, but if you have very few labeled nodes, it's the local methods that perform better. And many real-world networks can be constructed into signed networks. So continuing with this, it's unsigned node relevance has been extensively studied, but we're trying to push forward into the signed network domain. And we presented a few traditional measurements of past literature, and skipping for time. The future work, we're looking at modeling signed networks. So what we want to do is analyze and discover the different properties of them. And why would we do that? So it's trying to understand the underlying dynamics. We can also use it for impacts such as creating synthetic networks for benchmarks or for anonymizing social media networks so they can be released. Here is a set of many problems. And for sake of time, you can see our survey paper where, for example, the node classification and tie strength, the ones in red, are kind of these novel problems that haven't been studied in the past. And thank you to our supporter and the lab mates, KDD and MLG.